Welcome to part 2 of dimensional analysis. So in the first video, we covered what dimensional analysis is and how to get the primary dimensions from parameters. We also covered why it's important, how it's used, but in this video we're going to be covering the method of repeating variables and the Buckingham PI Theorem to actually get our dimensional analysis complete. So how I'm going to do this is I'm going to go through this problem and I'm going to solve it using the method of repeating variables and the Buckingham PI Theorem. It will take a little bit of time, so bear with me here. It's a long problem, but I want to make sure that everything is clear as day. And at the end, it says find the drag coefficient, the wind tunnel speed, and the aerodynamic drag in the wind tunnel. I will not be solving for any of those in this, as that would just take a little bit too long, but just know that there are relationships between the different pi's of the prototype and the pi's of the model. So pi 1 of the prototype will be equal to pi 1 of the model, assuming they are completely in similarity, which is the goal of this method. So let's go ahead and get to solving. So first of all, the Buckingham PI Theorem, what we're kind of looking for is something that looks like this. Pi 1 is equal to a function of pi 2, pi 3, just as many pi's as we need until we get to pi k. And what this allows us to do is say, hey, this we think is related to this in this way. And it allows us to cut down on everything, going back to part 1, why it's important, put all of that, right here. This is what we're kind of looking for, that we have pi 1 is equal to a function of all these other pi's. And our goal is to generate these pi's. And this method of repeating variables is how we generate the pi's. So let's go ahead and get started with step 1. So step 1, we want to list all of the parameters and count the number of parameters. So looking at the problem over here, we have a diameter of 20 feet, total weight of 145 pound force, terminal velocity of 18 feet per second. We have it so we're putting a smaller version of it, a factor of 12, into a wind tunnel at the same conditions. And the conditions that were mentioned in the problem were at 60 degrees Fahrenheit and 1 atmospheric pressure. So I got these two variables from a table in the book at 60 degrees Fahrenheit, 1 atmospheric pressure for the density and the kinematic viscosity. So why I got these instead of having a temperature, because if you remember from video 1, temperature is one of our main, one of our primary dimensions. We can express temperature inside of these two variables because fluid changes with temperature, with pressure, and as we were given the temperature and the pressure, we can now describe both of those in here for our density and our kinematic viscosity. So overall, for part 1, we are listing the parameters. So we're going to be having our drag force, our weight, the velocity we're traveling, the cross-sectional area, and I'm getting that cross-sectional area because we're given a diameter. I'm going to assume this parachute is a perfect circle, so this is just pi over 4 diameter squared. So that would be a cross-sectional area. Area is length times width. So that would be L2, but we'll get to that in a second. So our area, and then we also have our density of our fluid and our viscosity. So counting these, we have 1, 2, 3, 4, 5, 6. So we have our n value is equal to 6. Step 2. Oh, there we go. Step 2. list the primary dimensions of the parameters. So this is all from video 1 on how to do this slower. I'm going to kind of speed through this, but I'll kind of go through what I'm thinking as I'm doing it. So f of d is a force. This is our drag force, so this would be mass times acceleration. Our weight is also a force by nature. So exact same dimensions as our drag force. Velocity is some distance over time. So distance over time. Our area is going to be just L squared, so we discussed before, it's cross-sectional area, length times width, just two lengths put together, L squared. Our density is going to be a mass, so mass to the first power multiplied by length to the -3, because that is kilograms over cubic meters is an example of that. Lastly, we have kinematic viscosity. And kinematic viscosity is going to be mass to the first power multiplied by length to the -1 power multiplied by time to the -1 power. So this is normally in units of kilograms over meters times seconds, where meters and seconds are both in the denominator. So that's step 2 complete. We have all of our primary dimensions for our parameters listed. Step 3, we need to set the reductions j as the amount of unique primary dimensions, and we need to find the number of expected pi's. So what all of that means is we have some value called j, and j is just counting how many unique primary dimensions we have. So we have 1, 2, 3, and we don't have any more unique ones. If we had something like temperature or speed of light, or I should say the amount of light rather, the amount of matter maybe, but all we have right here is our mass, our length, and our time. So our j is equal to 3. And to find the amount of pi's that we need, we can just do k is equal to n from step 1 minus j, so 6 minus 3 is equal to 3. So we're going to be expecting 3 pi values. So from that very beginning part, we're going to have an expression that looks like this. So pi 1 is going to be a function of pi 2 and pi 3. So if k is less than 1, so if k is 0 or somehow k is negative, verify that you include enough parameters in your step 1. So k can be equal to 1, it can just be pi 1. In that case, it would just be, a constant. You can treat pi 1 as a kind of a constant, which we'll get to later on in the video. But this is kind of the idea of it. If you have k 1 or more, then you're good. If not, verify all your parameters from step 1. In this case, our k is 3, so we're expecting 3 pi, so we can move on to step 4. Step 4 is choose repeating parameters of a j amount. So we have 3 as our j value, so we need to choose 3 because that is our j value. So choose 3 repeating parameters. So repeating parameters, what all that means is that we're going to be going through pi 1, pi 2, and pi 3, and we're going to be changing out one of our variables. And the rest of them are going to be our j's. So this will be j1, j2, j3. It'll all make a little bit more sense as we go through the video, but our idea is that we have three primary dimensions we have to keep track of: our mass, our length, and our time. So for our repeating parameters, the general idea is that we have to make sure that number one, two repeating parameters are not the exact same. So our force or our drag force and our weight should not be together. Weight can be on there and force can be not on there, but if they're exactly the same, then that's just not great. The second thing, which is really crucial, is that we have to make sure that the length, time, and mass in our case, we have three up here that we need to include all of those within our three repeating parameters. And to make this a little bit easier, I'm going to select those as V, our velocity, A, our cross-sectional area, and rho, our density. The reason why I'm selecting these is that, first of all, our kinematic viscosity is a little bit long. It's 3. All of these are either 1 or 2 primary units in them, so that would just make our calculations a little bit shorter. But the main thing is that we have our drag force and our weight. So what will end up happening is something like pi 1 is equal to FD times VA rho, and then we'll have eventually pi 2 is equal to weight VA rho. But recall up here that we have our drag force and our weight, and both of them are forces. So we have m to the first power, L to the first power, and t to the negative 2 power. So our pi 1 and our pi 2 will actually be exactly the same if we do this. So since they are the same, then we can just calculate pi 1, and pi 2 will actually just be identical because we're using dimensional analysis. And in that, in part of the process, which we'll get to in step 5, is going to be solving to see where, in this case, our velocity, our area, and our density is. Again, the reason why I'm not choosing our viscosity, our mu value right here, is that it's just longer, and in our velocity, our area, and our density, we have our L, our T, and our M that we need to satisfy the requirement of having all three. So these are my three repeating parameters, and that's kind of why I've chosen those. So let's go ahead and get started with step 5, which is constructing the pies. So I'm going to go up here and mark that the velocity, the area, and the density are all repeating. So that's all those three arrows mean. So I just don't want to accidentally plug those in the wrong spots here. So how I'm going to do this is go from left to right up here. So we're going to start off with our f of d, move on to our weight, and move on to our viscosity. So pi 1 is going to be equal to m to the 0th power, L to the 0th power, and T to the 0th power. The reason why we're doing M, L, and T to the 0th power is because we have these three parameters, these three primary dimensions that we are trying to solve for. And our pi's are supposed to be dimensionless units, meaning we want all of these to be 0. We still want them to be there in some way, shape, or form, but they all have to cancel each other out, so it is a dimensionless number, such as the Reynolds number or the coefficient of lift or something similar. So going from left to right, we're going to be starting off with our drag force. So F of D is equal to our velocity times A1 times our area raised to the B1 power, and then times our density raised to the C1 power. And the goal of this is to solve for these exponents. So expanding this a little bit more, pi 1, let me carry all of this down, pi 1 is equal to our drag force, and we can see our drag force right up here as m1 L1 t to the negative 2. And now we multiply that by our velocity. So our velocity over here is right up here. This is our L1 t to the negative 1, which is raised to the A1 power. Our cross-sectional area right up here is our next step, so this would be L2 raised to the B1 power. And then we have rho, which is right here. So this would be M1 to the L negative 3 power, all of that raised to the C1 power. So what we're doing, again, is we're solving for A1, B1, and C1 such that this is true. Meaning what we can do here is we can separate everything into our mass, our length, and our time. So we're just going to be setting an equation and solving for all the exponents. And we can do this because everything in the masses will share a common base from our exponent rules. So we would have 0, which is coming from right here. So 0 is equal to 1. And then A1 doesn't have any mass, B1 doesn't have any mass, and C1 does have 1 mass right here. So this would be 1 plus C1. Our length is exact same process. We have L0, then we have 1, then plus A1, again just following all of the lengths only. So plus 2B1 minus 3C1. For the time, again, just rinse and repeat. 0 is equal to negative 2 minus A1, and that's the only time we have. So we just have to solve the system of equation. So C2 is equal to C1 is equal to negative 1. A1 is equal to negative 1, just from right down here. And then B1 is what we have to solve for. So let me actually move all this right down here. So B1 is what we're solving for next. So we have negative 1 minus A1 plus 3C1, all that multiplied by 1/2 is equal to B1. And we can just kind of solve this out. So this would be negative 1 plus our 1 right here. That'd be a plus 1. Negative 1 minus minus 1 plus 3 times a negative 1 over 2. So B1 is equal to negative 1 minus minus 1. Also, I know I should be able to do this in my head by now, but I'm currently fighting off a little bit of just allergies, so my head's not very clear. So this is negative 3 over 2. Let me just make sure I did all that correctly, because, you know, just head's a little bit not doing too good right now. So for our time, that should be, that explains a lot right here. So we have the negative 2 and we have this negative 1, and I put all of this as a negative 1 right here. So let's redo that. So that would be minus 2. And that would give us negative 2 over 2 or negative 1. So now we have our exponents. We have our b1, our c1, and our a1. So solving for our pi 1, we now get to use this expression right up here. Our force of drag is equal to v to the a1 power, a to the b1 power, and rho to the c1 power. So we have our force of drag is multiplied by our velocity to the a1 power. So a1 is right here. So we're just putting it on the bottom because it's a negative exponent. Then we have our b, which is our cross-sectional area raised to negative 1 power. So that's just putting it on the bottom. Then we have our density, which is just alone down here without anything else. So it's just to the negative 1 power as well. So pi 1 is actually really similar to the coefficient of drag. And the coefficient of drag, if you recall, is the force of drag over 1/2 rho v squared a, where a is some kind of cross-sectional area, which in this case we have. And what I'm going to do is move this just a little bit down here and say that pi 1 is going to be equal to my coefficient of drag. The reason I can do this is because the coefficient of drag is non-dimensional, as pi 1 is also non-dimensional. As these values are just all together and all of them will cancel each other out, since the coefficient of drag is a known number that we can use, we can kind of make an assumption in the sense that pi 1 is going to be equal to our coefficient of drag. So in the long way of saying pi 1 is our coefficient of drag. So all we did here was just add in the 1/2 because it is a known value that we can put into it to make it coefficient of drag. So next is pi 2. And for pi 2, we're going to be following this exact same procedure of solving our exponents, but I'm going to make this one very quick because, as we discussed previously, the drag force and our weight are fundamentally the exact same. So if we plugged in our weight for right here, then we would get the exact same dimensions right there, which means that we would go through all of this exact same solving to get our coefficient of drag. So I'm going to say that pi 2 is equal to pi 1 because the drag force is equal to, or the dimensions of the drag force rather, equal to the weight, the dimensions of the weight force. So therefore pi 2 is also going to be equal to the coefficient of drag. Lastly, we are going to be looking at pi 3. So pi 3, as we are going up here, remember left to right, we already solved for our drag force, our weight, and we only have one more to go, which is our kinematic viscosity. So we can start this off the exact same way as saying that be our mass to the 0th power, length to the 0th power, and time to the 0th power is all equal to our kinematic viscosity multiplied by VA2, or excuse me, A3, since we're on pi 3 now, multiplied by A B3 multiplied by our density, rho, to the C3 power. And it's the exact same procedure, so we're just going to do pi 3 is equal to all of this. And what I'm going to do to save a little bit of time is copy all of this over, because everything that I just copied right here is just this, just spelled out in terms of the primary dimensions. So go down here and change the exponents so they are A3, B3, and C3. And now in the spot where I put in the parentheses, we just need to have our kinematic viscosity, which is right over here. So let me just put that right into here. Hopefully that fits. Oh, it doesn't. That's too bad. So just move this over a little bit, give a little bit of room. So that is our kinematic viscosity. So now, exact same procedure. We get our mass, our length, and our time. And we solve. So mass is our 0, and then we have our m1, which is right here. So 1, we don't have any mass in our A term. We don't have any mass in our B term, but we do have mass in our C term. So this would be plus C3. Our length is 0, and then we have -1, then we have plus A3, plus 2B3, minus 3C3. Lastly, for our time, we have 0 is equal to -1, minus A3, again, so 0, -1, minus our A3. We don't have time in the B3 and the C3 term. So solving the system of equations, C3 is equal to -1, A3 is equal to -1, and then all we have to do is solve for our B3 term. So this would be 1 minus A3, so we put this in parentheses already, 1 minus A3 plus 3C3 to the 1/2 power, to the 1/2, just multiply by 1/2. Again, a little bit tired, a little bit out of it, my apologies, but hopefully all this is making sense. So we have all of this is equal to B3. Solving for B3 now, we have B3 is equal to 1 minus -1 plus 3 C3, which our C3 is -1. So this is 1 minus -1 plus 3 times -1, which is -1 over 2. So here we found our C3, our A3, and our B3. So plugging in, we have our pi 3 is equal to, remember using all of this up here, we have our kinematic viscosity, and our kinematic viscosity is multiplied by our velocity to the A3 term, so it would just be V on the bottom, and then we have our cross-sectional area raised to the B3rd power, so this would be A to the negative 1/2 power, so just put the square root over the a at the bottom. And then we have our rho term, which is at the bottom as well. So I'm going to clean this up a little bit in saying that our area, as you recall, our cross-sectional area, we defined it as length squared, right? So if we go ahead and we take the square root of our area, then that will leave us with our length. Because anything, just length squared, that would just take the square root of it and it just becomes length. So what we can do is say that pi 3 is equal to our kinematic viscosity divided by VL rho, which some of you may recognize is very close to the Reynolds number, or RE. So Reynolds number is really important as it is the inertial forces over the viscous forces. So the Reynolds number is actually just the inverse of all of this. We have our viscous forces, we have our inertial forces. So similar to what we did with our coefficient of drag with this whole 1/2, as we're just that close and we know that our relationship is right there, what we can say is that pi 3 is equal to our Reynolds number. So that is generally how you do dimensional analysis. So all we have to do at this point is, do I still have this at the top? Yep, all we have to do up here is plug in our pi 1, pi 2, and pi 3 to this general form. So over here, step 6 is to construct the final equation. So this is pi 1 is equal to a function of pi 2, comma, pi 3. So our pi 1, as you recall, is the coefficient of drag, is equal to the function of the coefficient of drag and the Reynolds number. So this is what I'm going to consider as the final answer. Again, the problem is asking for more in terms of what is it asking for? The drag coefficient, the wind tunnel speed, and the aerodynamic drag in the wind tunnel. But I did not know that was a picture. That's kind of cool. But at this point, what we can do is get, the drag coefficient, the wind tunnel speed, the aerodynamic drag in the wind tunnel, all of that through using this relationship that we have just found down here. Because the coefficient of drag, it is a function of itself, and it is a function that involves the Reynolds number. So all of that is true, which is what we're looking for, but the big thing that I do want to get out of this is that our pi 1 for our prototype will be equal to our pi 1 for our model. Our pi 2 for our prototype will also be equal to our pi 2 for our model, and our pi 3 for our prototype will be equal to pi 3 of the model. So what we're able to do is find these speeds and these numbers that we need to from using this idea that is all from what we have just found in this function.